Howdy, Brian Vikings. We're going to start our electrons unit by taking a look at light and see how light, what real light really is, and how it was. Now, if you started to think, how would you describe color to a blind person? That might be a little difficult. But hopefully, at the end of this, you might be able to describe it in a quantitative sense or describe it a little bit better. So, some key questions here we will understand is that we will understand what the electromagnetic spectrum is. We'll be able to label parts of a wave and describe what each part represents, and we'll know what the relationship between energy, frequency, energy and wavelength and frequency are. First, start by talking about the electromagnetic spectrum right here. So that's actually what this uh, part of what it is. That's showing you a little part, but here's a good numerical representation of it. So the electromagnetic spectrum is simply just all of light. So this is all light, but they are moving all at the same speed, but some of them have different wavelengths and by proxy have different frequencies. So over here we have the highest energy. We have the X-rays and the gamma rays. Those are the things that can hurt you and can really harm your body. And even ultraviolet light can still harm your body because it has a lot of energy. And then we get to the visible light, which doesn't hurt you. You see it all. That's what you need to see. All the light entering your eye. And infrared light does not hurt you, but anything that emits heat will emit infrared light. And then we get shorter and shorter, longer and longer wavelengths. So we end up getting down to the radio waves down here. So lots of good examples from that. We have, your cell phones use light. That's how we broadcast the signal. Radar, ultrasound, microwaves. Microwaves are light. You just can't see that light. Infrared light, like not the green one, but like the black and white one is called forward-looking infrared. You probably know what I'm talking about, black and white night vision. And then, things like PET scans and cosmic rays and X-rays are all light. The electromagnetic spectrum is really just a form of energy that exhibits wave-like behavior. So we'll start to really unpack what this is.
What if you could only see one color? Imagine, for instance, that you could only see things that were red, and that everything else was completely invisible to you. As it turns out, that's how you live your life all the time, because your eyes can only see a minuscule part of the full spectrum of light. Different kinds of light are all around you every day, but are invisible to the human eye. From the radio waves that carry your favorite songs, to the X-rays doctors use to see inside of you, to the microwaves that heat up your food. In order to understand how these can all be light, we'll need to know a thing or two about what light is. Light is electromagnetic radiation that acts like both a wave and a particle. Light waves are kind of like waves on the ocean. There are big waves and small waves, waves that crash on the shore one right after the other, and waves that only roll in every so often. The size of a wave is called its wavelength, and how often it comes by is called its frequency. Imagine being a boat in that ocean, bobbing up and down as the waves go by. If the waves that day have long wavelengths, they'll make you bob only so often, or at a low frequency. If the waves instead have short wavelengths, they'll be close together and you'll bob up and down much more often, at a high frequency. Different kinds of light are all waves, they just have different wavelengths and frequencies. If you know the wavelength or frequency of a wave of light, you can also figure out its energy. Long wavelengths have low energies, while short wavelengths have high energies. It's easy to remember if you think about being in that boat. If you were out sailing on a day with short, choppy waves, you'd probably be pretty high energy yourself, running around to keep things from falling over. But on a long wavelength sea, you'd be rolling along, relaxed, low energy. The energy of light tells us how it will interact with matter, for example, the cells of our eyes. When we see, it's because the energy of light stimulates a receptor in our eye called the retina. Our retina are only sensitive to light with a very small range in energy, and so we call that range of light visible light. Inside our retina are special receptors called rods and cones. The rods measure brightness, so we know how much light there is. The cones are in charge of what color of light we see, because different cones are sensitive to different energies of light. Some cones are more excited by light that is long wavelength and low energy, and other cones are more excited by short wavelength, high energy light. When light hits our eye, the relative amount of energy each cone measures signals our brain to perceive colors. The rainbow we perceive is actually visible light in order of its energy. At one side of the rainbow is low energy light, we see as red, and at the other side is high energy light, we see as blue. If light shines on us that has an energy our retina can't measure, we won't be able to see it. Light that is too short wavelength or high energy gets absorbed by the eye's surface before it can even get to the retina, and light that is too long wavelength doesn't have enough energy to stimulate our retina at all. The only thing that makes one kind of light different from another is its wavelength. Radio waves have long wavelengths, while X-rays have short wavelengths, and visible light, the kind you can actually see, is somewhere in between. Even though our eyes can't detect light outside of the visible range, we can build special detectors that are stimulated by these other wavelengths of light, kind of like digital eyes. With these devices, we can measure the light that is there, even though we can't see it ourselves. So take a step back and think about all of this for a moment. Even though they seem different, the warmth you feel from a crackling fire is the same as the sun shining on you on a beautiful day. The same as ultraviolet light you put on sunscreen to protect yourself from. The same thing as your TV, your radio, and your microwave. Now those examples are all things here on Earth, things you experience in your everyday life. But here's something even more amazing. Our universe gives off the full spectrum of light too. When you think of the night sky, you probably think of being able to see the stars shining with your own eyes. But that's just visible light, which you now know is only a tiny part of the full spectrum. If we had to draw the universe and could only use visible light, it'd be like having only one crayon. Pretty sad. To see the universe in its full spectrum, we need to have the right eyes, and that means using special telescopes that can help us see beyond visible light. You've probably heard of the Hubble Space Telescope and seen its beautiful pictures taken in visible and ultraviolet light. But you might not know that there are almost 20 space telescopes in orbit, missions that can each see part of the full spectrum of light. With telescopes acting as our virtual eyes, both in space and here on Earth, we can see some amazing things. And the coolest thing of all? No matter the wavelength or energy, the light that we see out in the distant universe is the same thing as the light that we can experience and study here on Earth. So since we know the physics of how X-ray, ultraviolet light, or microwaves work here, we can study the light of a distant star or galaxy and know what kinds of things are happening there too. So as you go about your daily life, think beyond what your eyes can and can't see. Knowing just a little bit about the natural world can help you perceive the full spectrum around you all the time.
So that was a great video, and they did a good job explaining the rainbow of colors that we see. And let's take a look just right here. We see that the highest energy, because these are the high energy ones, the highest energy is the purple ones right here. And then the lowest energy of the visible light is actually red. So a lot of people get that backwards. I think Crayola does a disservice to you by saying that these are like the warm colors over here. So people think that warm is high energy, and that's not true. Okay, so the high energy ones are going to be the purple ones, the violet ones. And another thing the video does say a lot is it said, and this slide actually does too, where it says a long wavelength and then a short wavelength. Those are okay, but I like to use the words high and low. So this is actually a low wavelength because when we start quantifying this and put numbers on it, it's easier to see like a lower number. So it has a lower wavelength right here, and this one has a higher wavelength. Okay. because the length is longer. It's higher. So that's just a couple of things I like to say instead. So I just thought I would throw that in there. So now we have light that moves. It moves at the speed of light, and here's your first number here. You need to make sure this is written down. I'm not entirely sure this is given to you in your notes, but this is a constant speed of light. It does not change, cannot change. In a vacuum, it is 3 times 10 to the 8 meters per second. Now, that is the fastest thing that can ever go. Nothing can go faster than the speed of light. Now, the it can slow down a little bit if it goes through air or it goes through water. The speed of light can slow down, but it cannot get faster than this. This is like the speed limit of the universe. So it actually takes 8 minutes and 20 seconds for light to move from the sun to the earth. And so that's kind of a long time, but the next nearest star, Alpha Centauri, it takes 4.367 years for light to get from that sun to us. So, and that's just the next nearest star. Some stars take billions of years. So, now, light is one of those special things that can behave both as a wave and also as a particle. So we call it a particle-wave duality. It's really kind of cool. It's more of a particle that moves like a wave, and we'll get more into this a little bit later. So, but we call these particles, we call them photons. And my professor used to always call them packets of energy. And so think of it just as a packet of energy that's moving like a wave. So we need to understand what a wave is. So on your notes, on page 2 of your notes, it's going to ask you to draw a wave, a picture of a wave. So this is what you'll need to draw, something like this right here. And then you have a wavelength and you have a frequency. Go ahead and add amplitude. And then now frequency wavelength is going to have the Greek letter lambda. That's a lambda right there. Okay, and then amplitude is an A, but not, okay. We won't really use the amplitude that much. Frequency is going to be the Greek letter nu. That is it. Nu, it's pronounced nu. Nu or F. So I will use the Greek letter nu for most of the time. So on your wave that you just drew, well, let's go ahead and label it. That is going to be the crest. That's the top. And then the trough. Now the resting position is right here. And now the wave length is the length that goes from crest to crest right there. There's another way to do a wavelength. You could do it from trough to trough, or you could do it from here to here. It is the same, but most people just go from crest to crest. The amplitude is going from the resting position to a crest or the resting position to a trough. They are the same. Now the amplitude is really mostly referring to sound. We don't really use amplitude when it comes to light. So wavelength. Its unit is a meter and is the distance between the equivalent points of adjacent waves, or it is the distance between crest to crest or trough to trough. So that's it. So which one of these has a longer wavelength? Well, it's the one on top, right? It's A. That one has the longer wavelength. So the amplitude, the vertical distance between the resting position and the crest. So that's it right there. And now the frequency is the number of waves that pass a given point in 1 second. So how often it's occurring. Now, and it's in seconds. So now, and it's number of waves per second. So the per second is called the hertz. Okay, so a hertz is 1 cycle per second. Okay, that's the same thing. So that's what we mean by hertz. So which one has a higher frequency? Well, that would be the one on the bottom, right? you're getting more waves, so you're going to get more frequency. So now frequency and wavelength have an inverse relationship. So what that means is as one goes up, the other one is going to go down. Now we're going to look at that simulation now. So let's take a look at it. If we're seeing this, we have we're going to change the dampening down to 0, and then we're going to have no end. And so now we'll oscillate this. So check it out. We're not going to mess with the amplitude, but if we increase the frequency, and it's going crazy right there, your eyes start to play tricks on you, and you will see that these little green parts looks like they're moving down the wave. But if you slow it down, you see that the green parts aren't moving at all. You're just moving them up and down. Now what's really, really cool is that I can pause this, and then I can bring up my ruler, and I've got my frequency already there. I'm getting 3 waves per second, and I can find the wavelength just right there. It's about 2 centimeters. So let's put that ruler off to the side, and now let's change the frequency. Let's cut it in half. Well, that's about half. And now let's do that. Let it go for a minute. We're going to pause right now. And then we're going to get the length again. And look, we cut the frequency by about half, and then the wavelength basically doubled. Okay? So as the frequency goes down, the wavelength is going to go up in a in an inverse relationship. See how that works? Yeah? Right? Okay. Now, whoops. Yeah. So they are opposites. One increases and the other decreases. So that is on page 3 of those notes. The frequency and the energy have a direct relationship. So what that means is that as one increases, the other increases. So frequency and energy are directly related. And then energy and wavelength are inversely related. So, which means that as one goes up, the other one goes down. So energy and wavelength are opposites. So let's, knowing that, let's see if we can compare these two. Now, which one, the wavelength. Let's just look at the wavelength right here. So which one is going to be the longest one? You were correct. That was the A, and B was the shortest. So what about the frequencies now? Which one's going to have a higher or lower frequency? Well, A is going to have a lower frequency than B. It should say lower, not higher, highest. Yeah, I'm sorry. This one should say, this one should say lower, and this one should say higher, not highest. So energy, this one will be the lowest energy, but this one will be the highest energy. Okay, that's all straight, good to go. Hopefully everybody's good to go on this. So let's understand just a little bit about the photoelectric effect. I'll go through this as quickly as possible. This is how Einstein won his Nobel Prize, is by demonstrating the photoelectric effect. So what happens is light comes in, hits a metal surface, and it will actually eject an electron. So he was able to understand this and study the frequency of these electrons being emitted, and he was figuring out that light was interacting with the electrons here, these photons were interacting with these electrons in the metal and then ejecting them. So that's quite interesting. So a light must have a certain amount of energy, right? So the more intense the light, the more electrons are ejected from the metal. And the higher the frequency, the faster the electrons go. So we know that light is a small packet of energy called quanta, right? That's where we get the word quantum from. It's quanta. And so a photon is a small quanta of light, or a packet of energy, right? We went over that before. So the color of light depends on the energy or the frequency of that photon. So the color depends on the frequency of the photon. So the red has the longest wavelength, and then violet has the shortest wavelength. Now red has the lowest frequency, but violet has the highest frequency, and then red has the lowest energy, and then violet has the highest energy. Okay? Remember, you have to put sunscreen on to protect you from ultraviolet light. That's because it has a high energy. Okay, so let's do a mastery check. Which wave has the shortest wavelength? Which wave has the highest frequency? Good. Now, which wave has the lowest energy? That would be D, because it has the longest wavelength, or the it has the longest wavelength or the highest wavelength. Okay? All right. Have a great day.